Hi, I'm the Big Lebowski. You've seen me in such fine quality, epic chemistry educational videos such as The Dude Abides in Chemistry and The Dude Loves the Ideal Gas. Okay, so this video is for working with the Ideal Gas Law worksheet that I gave out to my honors chemistry classes, and this is for those people who did not have an opportunity to go and work through a few examples of those. And like I said, this will be an opportunity for you guys to catch up. So this is pretty much it. There's a number of gas problems in here, and that's going to be due when we come back from vacation. But the idea is I'm going to work with some terms, and we're going to work through a couple of problems. So let's go ahead and let's get started. So hopefully this will be big enough for you guys that you can see this, that this is in fact the ideal gas law. Okay, and I'm going to put that up for you guys so you can see it. So given the ideal gas law, well, what exactly is the ideal gas law? We've looked at Boyle's, we looked at Charles, we looked at Gay-Lussac's law. And what we found was there was always something that was either kept constant, and we also looked at here's where you're starting, here's where you're ending. But in the ideal gas law, I call it the gas selfie, because we're taking a snapshot or a selfie of the gas at that moment in time. So what does that look like? Well, if we look at the ideal gas law, there is a formula called PV equals NRT. Now that's right on your worksheet so you can follow along with this. So what are the different parts mean? What does the P mean, etc., etc.? Well, P has to do with pressure. Now for us, for the ideal gas law, for this class, honors chemistry, we work with atmosphere. Okay, that's going to be our unit of air pressure. The V is volume. Now the volume in this case is going to have to be in liters. Can we work the problem with milliliters? Yes, but you still need to change it to liters. The reason for that is because we have to look at R, which we'll get to in a minute. Now, N is equal to the number of moles of gas that you have inside your container. T, okay, T is our temperature. Now our temperature is going to be in degrees Kelvin. Now remember, to change from Celsius to Kelvin, you add 273. To go from Kelvin to Celsius, you subtract 273. Now what is R? R is the universal gas constant. Now I'm not going to write the units up because the idea with those units, when you're doing calculations, they cancel a bunch of these other units out. But for us, it's 0.08206. This is our magic constant. Yes, you would have that on a quiz, on a test, on a final exam. I do not expect you to memorize PV equals nRT and 0.08206 for your gas constant. I don't. Okay? So let's go and let's look at a problem. Okay? So what pressure is required to contain 0.023 moles of nitrogen gas in a 4.2 liter container at a temperature of 20 Celsius? Okay, let's identify our parts here. So what pressure? Okay, guess what that means? That's what we have to find out. So our pressure is a big question mark. We have N, they gave it to us, it's 0.023 moles, okay, and we have a volume, that would be over here. Our volume is 4.2 liters. And then we have a temperature of 20 Celsius, but we have to change that to Kelvin. We absolutely have to. And in this case, guys, 20 plus 273 gets us 293 Kelvin. So that's what we have, ladies and gentlemen. So now we have our variables. We know we need to identify the pressure, which is going to be in atmospheres, okay? We know how many moles, we know the volume, and we know the temperature. You say, well, wait, what was there before? We don't care about before. We only care about now. What's happening? Because that's the ideal gas law. It is the snapshot, if you will. It is the snapshot. So, okay, what do we do next? Well, the next thing that we're going to do, ladies and gentlemen, is that we are going to solve the problem. We're going to write down our formula, okay? PV equals nRT. Now we're solving for pressure, so we can go ahead and we can just plug in everything. We know P is going to be X, so we're going to have X times 4.2 liters is equal to 0.023 moles, okay? That's where we write in the moles, multiplied by our beloved gas constant, 0.08206, multiplied by our temperature, which is 293 Kelvin. So what did I do? I took the numbers that we figured out here from the problem, and I plugged it into our formula. So X, which is our pressure, times 4.2 liters, our volume, is equal to N, the number of moles, times our constant R, times our constant T. Or we could look at it this way, PV equals nRT. So this is how it works. Let's go ahead and let's solve the problem. Okay, so 293 times 0.08206 times 0.023 equals, and I got a very small number like 0.55, but we're going to divide it by 4.2, divided by 4.2 equals, and we now have a new pressure, and our new pressure, ladies and gentlemen, is 0.132 atmosphere. Okay? This is one way that we can do that. Okay? Now, is there another way? Well, yeah, in that I could sit there and take this and just go ahead and say, hey, nRT divided by V is equal to P. I can do that. That's what we're interested in solving for P, which basically that's what I did here. I just multiplied these three numbers out and I divided by this number, which is what I'm showing up here. So this is taking care of our first problem, ladies and gentlemen. Okay? Hopefully this will help out. Now remember, you can also go back and review this. Oops. Let's look at our second problem here. So we have oxygen gas is collected at a pressure of 123 kPa in a container that has a volume of 10 liters. Alright, so I've got a pressure right here. I have a volume right here. What temperature? Aha! So we need to find out our temperature because it said what temperature. So that's what we need to find out. Must be maintained on half a mole of this gas in order to keep this pressure. And then the last twist is express the temperature in degrees Celsius. Okay. So if we look at it, what are the facts that we have? Well, we have pressure is equal to 123 kilopascals. This is not going to work for us. And the reason for that is because our constant R is based off of atmosphere. Now, is there a constant R for kilopascals? Yes. Am I going to give this to you? No. I don't want to confuse people. I want to stick with one value of R. That's it. And that value of R happens to deal with atmospheres. So we're going to have to change this into atmospheres. That's what we're going to have to do. Okay? Now, what else do I have here? I have a volume of 10 liters, and I have my N value of 0.5 moles. Now, my R value, well, that hasn't changed. It's 0.08206 pop. Like that. So we have everything. And of course, we have our faithful formula, which is PV equals nRT. That's it. So we have practically everything, but we do need to change this from kilopascals to ATM. How in the world do we go ahead and do this? Well, let's look at this, okay? I'm trying to gauge how far what I can do here. All right, so our first thing we need to do, we have to change kPa to atmosphere. That's our first thing. How do we do this? You're going to need the Vamos a la Playa chart. You'd say, well, Mr. Canu, did you put that on the worksheet? No. You're going to have to use your notes, or you could use the book, or you can look it up on the internet. Okay? So I have 123 kilopascals over, well, I don't know how many atmospheres I've got. Now, here's the thing. What do we have in common at the beach? Well, the air pressure is the same, but the units are going to be different. The number values of the different air pressure units will be different because they work on a different system. So in this case here, it's 101.3 kilopascals to 1 atmosphere. Where did that 101.3 kilopascals comes from? That is the air pressure at the beach, where the air pressure is the same, but we know that 1 atmosphere will equal 101.3 kilopascals. Okay, so let's go ahead and let's figure out our atmosphere. Okay, so I got 123 times 1, we cross multiply, and then equals 101.3 times x. Well, you know what? We're going to take 123 and we're going to divide it by 101.3. Clear this. 123 divided by 101.3 equals. So I end up getting 1.21 atmosphere of pressure. Okay, so now we figured out our first part. We're going to go ahead and we're going to move on. Now that we've figured that, we can now go ahead and plug it in. PV equals nRT. Well, what's our pressure? Our pressure is 1.21 atmosphere multiplied by, what's our volume? Well, our volume is 10 liters. Okay, so we'll have a volume of 10 liters is equal to, well, they said half a mole, I believe. Yep, half a mole. Okay, so 0.5 moles multiplied by R, which is our 0.08206, multiplied by T. Wait. T is what we need, so we're going to have to find out our T. That's where our X is going to be, times X. So I'm just taking the numbers we have, and we're plugging it in to PV equals nRT. Okay, so I got my atmospheres, I've got my liters, N is for my moles, okay, R is our gas constant, and T is our X, because that's what we're aiming for. All right, let's look at this. So I need 1.21 times 10 equals 12.1. Okay, so that's equal. 12.1 is equal to, okay, so 0.08206 times 0.5 equals, oops, try that again, 0.5 times 0.08206 equals. Okay, and that's going to equal 0.04103x. All right, so now we're going to take that and we're going to divide it out. Okay, so we're going to take our next step. If we look in terms of algebra, okay, we're going to go ahead and take the 12.1 divided by 0.04103, and that's going to give us our x. Okay, so again, it's just doing the algebra, and at that point, our x equals 294.91 degrees Kelvin. So that's our answer in Kelvin, but if we go back to our problem up here, it says express the temperature in degrees Celsius. So, last step. How do we change it from Kelvin to Celsius? Okay, let's look at it. So 294.91, we're going to subtract 273 Kelvin, and that, ladies and gentlemen, is going to give us our Celsius. So what am I going to get at the end? At the end, I'm going to get 21.91 degrees Celsius. This, ladies and gentlemen, is our final answer for this. Okay, and it's about room temperature for those of you who are wondering. Okay. Well, ladies and gentlemen, that's it for this video. I hope that this will help you out. I tried to spend the time on this, pointing out, tearing apart the problem. How do we tear apart the problem? Okay, and analyzing what are the pieces of information they give us in the problem, arranging the information that we have here with our formula, and then our temperature. Okay? All right, ladies and gentlemen, I'm signing off. Have a good one.